Okay, video number 2 for the improper integrals. I wanted to save one example, and it's very tedious and very long too, where we try to see if an integral is divergent or convergent. If it's convergent, what's the area between the curve and the x-axis through the unbounded region? I always say unbounded because there's an asymptote involved with these types of problems. So what I'm going to do is I'm going to go ahead and go right into the second example. I'm going to try to go slow and be very detailed. Let's integrate from 0 to infinity. X squared e to the negative x dx. This one should look familiar from integration by parts. We have an algebraic times an exponential. Before I convert the infinity to a letter b and let the limit as b goes to infinity apply, I'm going to leave the 0 and the infinity just the way they are. And when we get it all integrated out, because it's going to take a couple of rounds of integration by parts, but once we get it all done, then I'm going to do the replacement where we'll change infinity to the letter b, and we'll have a limit as b approaches infinity for each little part. Okay, so let's remember algebraic terms rank higher than exponential on the LIATE acronym. So I'm going to let x squared be u, e to the negative x dx be dv. Derivative of u, antiderivative of dv. U times v minus the integral of v du There is some simplification you can do along the way if you like. I'm just writing it all out because it's very tedious. The next step, I'm going to write those two negatives as a positive and also pull the 2 out. Okay, and then this is still an algebraic times an exponential. I'm going to let u be x, dv equal e to the negative x dx. Derivative of u, antiderivative of dv. Now this will only apply to the ending part right above it, that integral from 0 to infinity of x e to the negative x. That first part where we had u times v, that's already set in stone. I'm going to move to the next slide and expand that last integral. Okay, so we had plus 2. Now we got to do uv and that's from the second round of integration by parts, minus the integral of v du that will also have to be evaluated in 0 and infinity, minus the integral of v du Okay, so that's the integration by parts round 2. Okay, so now let's distribute the 2 through that back set of brackets and clean up signs, and then we'll start heading towards the limit part and see if we can get this thing to come out either it's got to either converge or diverge, but we'd like to see a finite value if we want a convergent improper integral. So we've got negative x squared e to the negative x. I'm just recopying. Okay, distributing that 2. Those 2 negatives make a positive 2. Very tedious. Okay, the antiderivative for e to the negative x is negative e to the negative x. So we've got a negative 2 e to the negative x, 0 to infinity. Okay, I'm going to concentrate on these first 2. Okay, so if we think of infinity as b, and again, I'm going to save the very back for the next slide. Probably going to run out of real estate on this one too. We have negative b squared e to the negative x, if you use an exponent property, is e to the positive x if it's moved to the denominator. Minus, and then we go back through and we sub in a 0. Minus negative 0 squared over, and again, e to the negative x is equal to 1 over e to the positive x, so that's e to the 0 minus now we'll look at that middle part, negative 2b over e to the b minus negative 2 times 0 over e to the 0 Okay, so that was the middle group, subbed b minus subbed 0. Let's recall e to the 0 is 1. Anything multiplied by 0 is 0. By L'Hopital's rule, that fraction, if b goes to infinity, and you have to use L'Hopital, that's where you take the derivative of top and bottom separately. Keep reevaluating until you no longer get infinity over infinity for this kind of rational expression. This will go to 0 because exponentials outrun quadratics. The faster, or excuse me, the larger you make x, the larger an exponential gets as opposed to a quadratic. 0 squared, that's 0, so that forces that one to 0. Okay, so that one was from L'Hopital's. The second fraction, just because 0 is your numerator, that's 0. In the back part, infinity, again, using L'Hopital's. Exponentials are faster, grow faster than linear, because that's a b to the first on top. That's going to go to 0. The second fraction, negative 2 times 0 is 0, divided by 1, still 0. So everything has gone to 0 so far, except we haven't applied anything to that third group. Let's do that now. Excuse me on the straight mark, y'all. All right, let's get to it. That third group, if we remember correctly, we're going to have limit as b goes to infinity. And it was negative 2 e to the negative x. Evaluated at infinity and 0. Let me do better than that. That needs to be a b. Yeah, there we go. Okay. Factor out the negative 2. Rewrite e to the negative x as 1 over e to the x. You don't have to factor out the negative 2, but you absolutely can. Whatever helps you see the progression better. Okay, subbing in, we've got negative 2. Limit as b goes to infinity. 1 over e to the b minus 1 over e to the 0. As b goes to infinity, the first fraction will go to 0. Make sure you see that. We have a fixed numerator, a denominator that's getting larger and larger, so that will go to 0. E to the 0 is 1. So 1 over 1 is 1. All of that becomes negative 1 times the negative 2 out front makes positive 2. And since that's a finite number, the original problem is convergent.